Hi students, welcome back to Civil Ed. I am Professor SPN from Civil Ed team. In our previous video lecture, I had presented the way of solving numerical problems on ladder friction. In this video presentation, let's solve numerical examples on wedge friction. So to begin with, let's look into the first problem. It says, in the figure shown below, a stone block weighing 6000 Newton is raised slightly by means of two wooden wedges A and B with a force P on wedge B. So a sketch has been provided for this problem. So let's see that. We have two wooden wedges A and B which are used to raise a stone block C weighing 6000 Newton. So A and B are wooden wedges over here, and these two wedges are used to lift a stone block having 6000 Newton weight in the upward direction. So they have also mentioned in the problem B with a force P on wedge B. So that is, the wedge B is applied with force P, and this, due to this application of force P, this wedge is moved forward in the right direction, and this causes the uplifting of this particular stone block C. So you can just observe that. So due to the application of force P on the wedge B, the block C will be lifted upwards. So it is also given in the problem, the angle between the contacting surfaces of the wedge is 5 degrees. So all the contacting surfaces are at 5 degrees to inclined to horizontal. So that's what is given in the problem. And if coefficient of friction is 0.3 for all contacting surfaces, that is mu value is given 0.3, compute the value of the force to be applied, that is P, to impede upward motion of the block C, that is to lift this particular stone block C. What is the value of force P to be applied on the wedge B? That's what is asked. Neglect weight of the wedges, that is the wedges A and B, their self weight can be neglected. That is what is given in the problem again. So to begin to solve this problem, I wish you people recall some theory on friction. So those who have not seen our previous video on friction, please observe the theory being explained over there, and that is of some use in solving problems on wedges. So to have a glimpse of that to you people, I am just explaining a small portion of that over here. So you know that any weight placed over a contact surface develops a normal reaction at the contact surface, and if this weight is pulled or pushed by means of an applied force, then there comes into picture a frictional force F in the opposite direction of the applied force. Now we had also learned that if we try to find a resultant of the normal and the frictional force, we can represent it by the letter R. And when the frictional force F reaches limiting frictional value, then the value of a limiting frictional angle between N, that is normal reaction, and R will be represented by alpha, and it is called the angle of limiting friction. So this concept we will be using in solving problems on wedges. So those who are not seen or those who are not looked into the theory of friction, please go back and view our lecture video on theory of friction. So to continuing with the problem, let's begin to draw the free body diagram for this entire arrangement of wedges and stone block. So we consider the floor level and the vertical wall as such. At the lowermost level we have wedge A, in between we have wedge B, and of course we have the stone block C at the top. The weight of stone block C is given in the problem, that is 6000 Newton, that we take as it is to be acting vertically downwards. Please note that we don't have any self weights of wedges A and B because it's given in the problem to neglect the weights of the wedges. Next, to begin with, I'll start to draw the free body diagram for wedge B first. So I'll consider the force P to be acting towards the right side, and I'll just begin the lower surface of B. I'll consider the lower surface of B now, and of course due to its contact with wedge A, you will have a normal reaction force acting towards the inclined surface of B, and please note that this inclination of the normal reaction with respect to the true vertical will be equal to 5 degrees. Why? The reason is all the inclined surfaces of the wedges are inclined at 5 degrees to horizontal. That's what is given. So the normal reactions will also be inclined at 5 degrees with respect to true vertical. And continuing, you have the frictional force in the opposite direction of the applied force P, and you are required to consider the resultant of the normal reaction and the frictional force for solving problems on wedges. So the inclination of the resultant force with the normal is represented by alpha, and it is called angle of limiting friction. That's what I have explained you in the previous slide, and I will call this resultant force as R1, and due to the contact of A and B together, a same resultant R1 will act towards the wedge A also. Please note that the resultant R1 towards the wedge B and A is the same. Next, moving on to the upper surface of the wedge B, I will consider that normal reaction first. Again, this normal reaction is inclined at 5 degrees to pure vertical, that is true vertical. Next, we have the frictional force in the opposite direction of the applied force P, and in between that we can have the resultant of the frictional force and the normal reaction, and I will call it as R2, and of course the angle between R2 and the normal reaction is alpha, that is angle of limiting friction. Please note here all the black arrows represent normal reaction forces, the orange half arrows represent frictional forces, and the blue arrows represent resultant of friction and normal reaction, that is represented by R1 and R2 in blue color. Please observe here, and the same R2 is acting towards the block C also, as we did here, the same way. And now let's look at the contact surface of C with the vertical wall, and we have this normal reaction. Again I am using black color here, and frictional force. Frictional force is, I am marking it in the downward direction. Why? The reason is due to the application of force P on the wedge B, the stone block C will be lifted upwards. So for that reason I show the direction of the friction, that is this orange colored line, arrow. So this is the frictional force in the opposite direction of the motion of the stone block C, that is the motion of stone block C is in the upward direction, and so I draw this frictional force I show in the downward direction. Please don't get confused with this self weight acting downwards, and don't say frictional force will be in the upward direction. Please don't say that. Due to the applied force P on wedge B, block C will be lifted upwards, so the frictional force is downwards. And again, in between this frictional force and the normal reaction at the contact surface of C, you have this reaction, resultant of the resultant force between the normal reaction and the frictional force, and I'll represent it with the alphabet R3, with the letter R3. And please note that again the angle between normal reaction over here and the resultant of normal and frictional force, that angle is alpha, angle of limiting friction. Now let's calculate this value of alpha. That's what is important over here in this entire free body diagram. Angle alpha is unknown. Let's use the known equations, that is coefficient of friction mu is equal to F by N. Also we know that angle of limiting friction represented by alpha is obtained by tan alpha is equal to F by N, and therefore we can say, with this, comparing these two equations, we can say tan alpha equal to mu, or alpha is equal to tan inverse of mu. So that gives us the value of alpha to be equal to 16.7 degrees, where mu, that is coefficient of friction, is 0.3 given in the problem. Please remember this formula only, alpha is equal to tan inverse of mu, for obtaining the value of alpha over here. Whether you write this entire thing in the exam, if you have time you can write, otherwise you can just remember this formula, alpha is equal to tan inverse of mu, and this works out to be 16.7 degrees. So let's use this value in the solving of the problem. So next, to continue with the problem, I will choose the free body diagram of block C alone, and I will try to find the unknown values. So just I am bringing the free body diagram of block C alone over here. Please note that the self weight of C acting downwards, that is 6000 Newton. The resultant R2 acting in the upward direction towards C, so that I am marking it here, R2. Of course the angle of inclination of R2 with respect to normal reaction is alpha, and with respect to true vertical it would be alpha plus 5 degrees. Please observe here, inclination of R2 with true vertical is alpha plus 5 degrees. That's what I have written here. Next, this is R2 and this is 6000 Newton I have written, remaining with R3. So that also I will draw here, R3. What is the angle of inclination? Angle of inclination of R3 is alpha with respect to horizontal. So same thing I will write here, alpha with respect to true horizontal. So these are the three forces acting on the stone block C. please note that we are not considering normal reaction and frictional forces over here. We don't consider them at all. Instead, we are considering the resultant of normal and frictional forces. For solving problems on wedges, you should consider only the resultant of the normal and frictional forces. So we have these three forces acting at the stone block, that is C. Now there are three concurrent force system these three forces represent a concurrent force system. So I can easily apply Lami's theorem to get the solution, for which I need to obtain the angles between the forces. So the angle between 6000 Newton and R2 works out to be 158.3 degrees. How? So this entire thing is 180 degree, this entire line, straight line, vertical line is 180 degree, minus of this alpha plus 5 degree. If you do, you get the remaining angle 158.3 degrees. Next, the angle between R2 and R3 works out to be 128.4 degree. How do you get that? So alpha plus 90 degree plus alpha plus 5 degree. If you do that, you will get 128.4 degrees. Next, remaining angle, you can either do 360 minus these two values, or you can just do 90 degree minus alpha. You will get 73.3 degrees. That is 90 minus 16.7 equal to 73.3. What is this 16.7? It is nothing but the value of angle of limiting friction alpha, which we have found in the previous slide. Next, moving on, we will apply Lami's theorem for this entire concurrent force system. So magnitude of any force divided by sine of the angle of other two forces is directly proportional for all the forces. So that's what is Lami's theorem. R2, this is R2 divided by sine of 73.3 degree. Next, R3 divided by sine of the opposite angle, that is 158.3 degrees. That will be equal to 6000, that is the third force, divided by sine of the opposite angle to 6000 Newton, that is 128.4 degrees, this entire angle. So this gives us the value of R2 and R3 to be equal to, R2 is equal to 7333.14 newtons and R3 2830.8 newtons. On solving this Lami's theorem equation, we get these answers. So next, further, let's move on to the free body diagram of B. So now I will consider the free body diagram of wedge B separately to find the remaining unknown forces. So I will consider the horizontal and vertical axis, and the first force I will imagine at the wedge B is the applied force P on wedge B acting towards the right. The next force is R2 acting towards the wedge B in the downward direction. So that's what I am bringing it here, and of course its value is equal to R2, which we have already found, to acting towards C, and it is same acting towards B also. And the angle of inclination of R2 with vertical, just observe here, alpha plus 5 degree with vertical, R2 with vertical, it is alpha plus 5 degree. So that's what I will write here. The next force R1 acting towards the wedge B, again its angle of inclination is alpha plus 5 degree with respect to vertical. So that's what I will write here, alpha plus 5 degree. So again these are the three forces which we consider at wedge B, and please note that again I am telling you, don't ever consider the normal and frictional forces at all, because instead we are considering the resultant of those two forces. So now to apply Lami's theorem, I will find the angles between two forces each. So angle between R2 and P works out to be 111.7 degrees. How? So this is 90 degree plus alpha plus 5 degree again. So 90 plus alpha is 16.7 degree plus 5 works out to be 111.7 degree. Next angle between R1 and P, again it is 90 plus alpha plus 5 degree. So that's what you get, same, these two are same. I think the reason is the angle of inclinations are same, and these two angles works out to be of same values. Again the angle of inclination between R1 and R2, you can either subtract with 360 degree these two angles, or you can just get it by subtracting 180 minus these and these two values. So I have taken 360 degree minus this angle and another one angle. So this works out to be 136.6 degrees. Now having known all these things, we will apply Lami's theorem. So Lami's theorem, what does it say? The magnitude of any force is proportional to the sine of the angle between other two forces. So P divided by sine of the angle between other two forces, 136.6 degrees, that will be equal to R1 divided by 111.7 degrees, that will be equal to R2 divided by another opposite angle, that is 111.7 degree. Solving this equation, we get the value of P, and again this R2 is already known, so 7333.14, this we had found when we considered the free body diagram of C. That value, if you substitute here, you get the values of P and R1 as this is what and this is what the required force P required to create an impending motion of the block C. So that's what we have found, P to be equal to 5422.81 Newton, and R1 again another unknown 7333.14 Newton. So this completes problem number 1. Moving on to problem number 2, we have two blocks A and B weighing 15 kilonewton and 3 kilonewton respectively are held in position against an inclined plane by applying a horizontal force P as shown in figure. So please observe here, two blocks A weighing 15 kilonewton and B weighing 3 kilonewton respectively are held in position against an inclined plane. So there is a difference between the previous problem and this problem. There you had a vertical plane, and here you have an inclined plane to which the blocks are resting, towards which the blocks are resting, and this angle of inclination is given to be 75 degrees, and of course the contact surfaces are at inclined at 10 degrees with respect to horizontal, and you are required to find the horizontal force P to cause impending motion of block A. So that's what they have asked here. And again one more information is, angle of friction for all contact surfaces is 12 degrees. So in the previous problem you were provided with the coefficient of friction mu, wherein you found the angle of limiting friction, but here directly they have given you the angle, that particular angle, that is 12 degree. And with this information, I wish you people to take this as an assignment problem and solve this problem. Kindly observe the problem number 1 completely once again, and take this problem to solve on your own, and keep updated by subscribing to our channel, so that you get the solution for the assignment problems also. With this, we have come to the end of this presentation, and now I wish you all share these video links with your friends also, and ask them to subscribe to get updates regarding the further videos. Thank you.